Hysteresis is a term that's been around for a long time. The phenomenon was identified and the term was coined by a Scottish physicist named Sir James Alfred Ewing in 1890. Hysteresis is a property of physical systems that do not instantly follow forces applied to them, but react slowly or do not return completely to their original state. You've all experienced hysteresis. For example, in these modern viscoelastic foam mattresses, if you were to push your hand down rapidly and retract it, you would see the shape of your fingers slowly recovering to the mattress's original shape. That is a hysteresis phenomenon. The term is used quite frequently in architecture to describe a property of building materials, in engineering, and in physics in general. Corneal hysteresis specifically is the term that we have coined. Dr. David Luce, PhD at Reichert, coined this term, and it is specifically to describe the difference in the inward and outward applanation pressures as obtained during the dynamic bidirectional applanation process employed in the ocular response analyzer. Mathematically, hysteresis, corneal hysteresis, is simply P1, applanation pressure 1, minus P2. It is the raw difference between those two applanation pressures. This is a new ocular parameter. It is something that has not been measured before historically, and when we first discovered this phenomenon, we didn't know exactly what it was. Could have been a machine artifact. It could have been something other than a real physiological descriptor of a property of the cornea. So we started to look at other measurements to try and find out what does this hysteresis property correlate with. The first thing we looked at was a number of subjects, and we compared the right and left eye value of this corneal hysteresis property, and we found there is a very strong relationship between right and left eyes in normal subjects. That's a good sign that this is a real biological marker, because corneal thickness, for example, is extraordinarily similar in right and left eyes of normal human beings. So you would expect, if this is a real property that we're measuring, that it would be very, very highly correlated in right and left eyes, and that is indeed the case. What is this hysteresis measurement a function of? Is it a function of the radius of curvature of the cornea? And in fact, there is no relationship between the radius of curvature and the corneal hysteresis measurement. Is it a function of astigmatism? Well, here's the narrow range of astigmatism, but there's a very, very low correlation between the hysteresis property and corneal astigmatism. What about intraocular pressure? Here's 339 normal eyes measured by Goldman tonometry and compared to the corneal hysteresis measurement. And this is a very, very weak correlation, even though that looks like a positive relationship. The R-square value in this data set is about a 0.0065, so there's essentially no relationship between the pressure in the eye and the corneal hysteresis measurement. We took this one step further and we said, let's look at the same eyes, the same corneas, and look at changing the intraocular pressure to see if this hysteresis phenomenon changes as a function of the pressure in an eye. And so what we did is we took 32 volunteers and we measured their pressure on Goldman tonometry, and we measured their hysteresis with ocular response analyzer. And then we took these same eyes and we applied force to the sclera with a device called an ophthalmal dynamometer, which raises the intraocular pressure, and we repeated the Goldman measurements and repeated the ocular response analyzer measurements. We did a third test where we pushed on the sclera a little bit harder, raised the intraocular pressure even more. So what we have now is we have the same corneas, and we're measuring their intraocular pressure and their corneal hysteresis at 3 different pressure levels: baseline, elevated pressure level 1, and elevated pressure level 2. And what we found was that on average in this population, even though the intraocular pressure was being elevated significantly, up to 40 to 50 millimeters of mercury in the final pressure level, the hysteresis was not changing much as a function of this change in intraocular pressure. So what we have here is a new indicator of a tissue property of the cornea that is not an artifact of any other variable that we have previously understood in ophthalmology. The one thing that hysteresis is correlated with moderately is central corneal thickness. This is important. Central corneal thickness is, prior to corneal hysteresis, one of the only biomechanical property indicators that we could get our hands on. The thickness of the cornea is indeed a biomechanical property of the cornea, but it does not provide a good overall representation of the total biomechanical properties of the cornea. And this is very important to understand because the thickness of the cornea is very important in ophthalmology and optometry for a number of different things. It's important for determining whether somebody is a good candidate for refractive surgery. And more recently, in the past 10 years or so, it has become important in determining the accuracy of intraocular pressure measurements because it's believed that a thicker cornea will cause a Goldman tonometer to read artifactually high, and a thinner cornea will cause a Goldman tonometer to read too low. This is extrapolating the idea that the thickness of the cornea must be related to its biomechanical properties and therefore its resistance characteristics. And what you can see here by looking at these two parameters, corneal thickness and corneal hysteresis, is that even though it's a positive correlation, that is, thicker corneas tend to have higher hysteresis and thinner corneas tend to have lower hysteresis, it's a very weak positive correlation. And there's a lot of scatter in the middle in these normal eyes that we're looking at in this particular example. So what that means is that corneal thickness in and of itself is not an accurate representation of the overall biomechanical properties of the cornea. And as such, maybe we've been depending upon corneal thickness a little bit too much for decision making that really should be where biomechanics really should be taken into consideration. Problem is, we didn't have an instrument to measure those biomechanical properties before. We do now.